All right, now we're going to start talking about some really interesting uh, objects to study in three-dimensional vector calculus. So Green's theorem was all about two-dimensional vector calculus. We're moving back up to 3 dimensions. So the first one we're going to talk about is the curl. The curl is a movement that bros like to do in the gym. Just kidding, that's a terrible joke. Curl is a thing in math. Let's remember the gradient. So if you had a function, f of x, y, z now. So if you were to graph this function, you would need to graph it in 4 dimensions. We sometimes had f of x, y, but let's do 3-dimensional calculus. Then we denoted that del of f, and that was partial of f with respect to x, comma partial of f with respect to y, comma partial of f with respect to z. Okay, and we could have just left it there, but mathematicians like to abstractify everything, including operators. So some mathematician came along and said, let's just write this as this way. Partial with respect to x, partial with respect to y, partial with respect to z, and then we'll put the f out here. And they said that means the exact same thing. It almost looks like f is a scalar, but that's not true. This isn't really a vector. So then we can, over here, define del to be this weird vector calculus operator. Partial with respect to z. This is a term I made up. It's not actually called this. It's a vector calculus operator. What does that mean? It's an operator, meaning it applies to functions. It produces a vector. It's not really a vector because these guys aren't numbers. And calculus because there's calculus stuff in it, partial derivatives. Okay, why do that? Because we want to go crazy and do other things with del. Okay, so that was gradient. We fully studied gradient. And now let's study curl. So curl, gradient took a scalar function. Curl is going to take a vector field, f. And then before we were using p comma q, we're now going up a dimension. So it's going to be p comma q comma r, where r should not be confused with any regions that we used before. Okay, and then the curl of that vector field is del cross f. Oof, what does that mean? Okay, del is a vector operator, which can be treated like a vector. And then f is a vector field. So remember how to do cross product. We take I, j, k in the top row, and then we put the first vector. Yikes, it's not really a vector, but let's do it. So we'll just write del in the second row. Nope, not partial anything. Partial with respect to y, partial with respect to z, and then we'll write our second vector in the third row, p, q, r. Okay, so this is weird. So what does this end up being? We have, so we take I times the determinant of that 2x2 submatrix. So that's just going to give us our first component. So we'll take partial r with respect to y minus partial q with respect to z. So if a function and an operator get multiplied, basically apply the operator to the function. That's what we're seeing here. Okay. And then remember these signs for determinant. So we got to alternate signs. So this is comma, negative, and then we cross out that row and column, take that 2x2 determinant. So partial r with respect to x, comma, partial p with respect to, not comma, minus partial p with respect to z. Be careful of what we're doing. Okay, this is a vector, but then all the components have to be scalars. That's good. Otherwise, we'll be lost. Okay, and then last one, we're back to positive sign. Cross out that row and column, determinant of that 2x2 minor partial q with respect to x minus partial p with respect to y. Okay, so that's the long form of the formula for curl. No one wanted to write that all out, so they wrote it like this. And Really, I don't know historically, but I suspect that this thing kept coming up, and then they realized that if they defined del as this vector operator, then they could just write it as a cross product, and it was easier. Okay, and then you can distribute the negative sign and simplify that. So what does curl mean? Curl tells you the amount of spin in a vector field. So let's say you have like water or wind vectors. Like in this one, let's say water vectors. This would be a whirlpool, and this would be just kind of like a current moving in one direction. Okay, so let's calculate the curl of these. So we have this vector field. Then we need del cross negative y x 0. So that's the determinant. I think it's easiest just to write it as a determinant, partial with respect to x, partial with respect to y, partial with respect to z, and then negative y x 0, right? Okay, so first component, cross out that row and column, take the determinant, so 0 minus partial of x with respect to z. Well, x doesn't depend on z, so that's going to be a 0, comma. Okay, so this is not too terrible. Now we cross out that row and column, and we have a negative sign. Okay, determinant of that minor, 0 minus negative partial y with respect to z. Well, y doesn't depend on z, so that's also 0. Okay, great. This is going well so far. And then the third one, we cross out that row and column, and then take the determinant of that 2 by 2 minor. We have partial x with respect to x, which is 1, plus, or minus, negative, so plus, partial y with respect to y, which is 1. Okay, so I get the curl, and you might get functions of x and y here if you had more complicated things. So the curl might be different depending on x, y, and z, actually. The curl might be different depending on the point you're at in R3. But in this case, it's a constant curl. And what that means is the amount of spin is 2. And actually, what you can see is if you do the right-hand rule, so if you curl your fingers in the direction that the vectors are going, then in your right hand, then your thumb points up. I'm doing it, but you can't see because the video is of the OneNote. Thumb points up, in fact, and that's the direction of your curl vector. Okay, so that's kind of cool. Let's just do one more example. So here's your current vector, 1, 1, 1, 0. Let's do, so it's curl cross 1, 1, 0. Let me actually make it more interesting than this. Maybe we'll make it x, y, 0. Okay, so that just means these get bigger as we go out. Okay, so we're not doing 1, 1, 0. We're doing x, y, 0. Okay, what happens? Are we spinning at all? Okay, so we have I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, x, y, 0. And then we take those 3 2 by 2 minors. So that's a 0, comma, that one's a 0, comma, this one is also a 0. Partial with respect to partial y with respect to x, and partial x with respect to y doesn't do anything. Okay, so great. It doesn't matter if the current is constant or if it gets bigger as you go out. As long as there's no spin, meaning you can think of this as the vectors interacting with each other, right? So you would need like a y or a z in the x component to make a non-zero thing here, because then the partial gets crossed with the other ones, is what happens.